That's pretty cool. You can see the bands better when you're in front of the thing, but you can't see the.
This one also is labeled as mercury.
What? That one?
HG is mercury, right?
Yes.
Yep. So the labels on the tubes are accurate, I believe. The labels on the tubes, sorry, the label on the glass tube is accurate. The labels on the cardboard tubes are not.
That's so cool. See?
I'm gonna take a picture.
So that's,
So they're both mercury. This is another mercury.
how do you
It's on
pronounce
Auto. I
the,
thought it
not
wasn't
the
gonna do it.
original, the, elements that they use instead of mercury, like, hide,
Oh, I don't know.
oh,
Dude,
What's that?
what,
this was in the water vapor tube.
Heck yeah.
what is that? That is,
Yeah.
Oh,
It's got the same thing. So
I gotta take a look here.
Oh, you are?
that is
This way.
weird.
Not too much light pollution.
Seems to be a unit.
The electro is a little bit smaller,
Is it?
but yeah, it should.
Yeah. Green is definitely the most dominant one, but then again, as we know, our eyes are much more sensitive to 555 nanometers. I think that's the optimum.
Yeah, well, that's very stabilizing. Did you drop it?
I wonder how hot this one is.
I think I tried that one, and that was black, but
There's not as much room to hold on to with this one.
yeah, let's find out what happens. You know, if it blows up, it blows up.
What is, why is it shaped like that?
I don't know. I was rummaging around and I found it.
Oh.
5,000 volts. It should just punch through like that.
HG.
That's crossed out.
Ooh,
What?
check that out.
A lot of nothing.
Oh.
What does it look like? Nothing.
I'm gonna turn off the light just to see if there's even the hint of a glow,
Yeah, this is the mercury.
or if we just have a little death trap right there.
Oh.
Any hint of a glow?
I'm not seeing anything.
I'm not seeing anything.
All right, so let's turn that off. Yeah. At one point, I put in a request for new tubes. The ordering process at the school still sort of baffles me. I put in the request, then it doesn't get put in within a certain right amount of time, and so they don't put in another request for another year. And then I think, I put in the request, surely they'll put the order in, and they don't. It's as if it never happened.
Nice.
If you miss the deadline, you never put the
Oh,
order
this
in.
is.
I was wondering about that with the laser, because little laser pointers aren't super expensive, so I was wondering why the blue one, like why we just didn't order a new blue one.
Yeah, that was also part of I think the order got in like a couple days after the deadline, and therefore it was as if they were never put in. They don't buffer it.
That'll teach you.
Yeah, actually, apparently it doesn't teach me.
This is the one.
All right, so if we go to Firewire,
Another better.
yeah, we got it. That's time to do this.
Man, this needs like, we would just put a 5,000. It's like 5,000. I was going to get people here.
I think it's going on.
Just did a video that guy that made like his own light bulb. And it's like a mercury, he like a megawatt light bulb in his house. And he turned it on, he like turns up the dimming switch and you just see his house disappear in light. He has
It's like the sun.
Yeah,
So
he
he
has-
has the sun in his house.
yeah, he has a camera outside, you just see the
Oh.
light.
One other thing while that thing's warming up. We had this number right here of negative 2.17 times 10 to the negative 18th joules. I rarely actually see that number if you were looking at atomic spectrums. That's generally not the number that comes up. They generally convert it to another unit, so negative 2.17 times 10 to the negative 18th joules. Electron volts is the more typical number of, and so 1 electron volt is equal to 1.6 times 10 to the negative 19th joules. And so if you take this number right here and divide by 1.6 times 10 to the negative 19th, you should get negative 13.6, I think it is.
I can, I could, try.
Okay, thank you. If you just do the 2.17 divided by 1.6, that'd be good enough.
Even though there's, even
Yeah,
though-
the 10 to the negative 18 over 10 to the negative 19 is the same small thing.
Negative 1.35625.
Okay, so we're on top of that. All right. So generally you see the negative 13.6. All right. So we did helium.
And mercury.
All right, so we have hydrogen here.
I'm trying to see. Where do you find?
To the outlet.
Oh, does it not just stay down the conduit?
It stays down about once every 100 times.
Good.
She was killed, one of the lights, please. Hold the light. Sure. Oh, yeah, that one. All right, so we've got the emissions of helium. So we had the yellow band. So for helium, we had yellow, green, blue, red. So I think we definitely saw that one. There's the red one. I do need to kill those lights. Now they don't have the numbers here, but that's the red one that we saw. We saw one of these green ones and probably saw that blue one right there. There are charts out there where you can actually look up the intensity of the light and what the actual wavelength is. And then,
Then there was mercury.
assuming these will be hydrogen, helium, mercury, there we go.
Oh, yes. The sun into.
So helium is right here where my cursor is. And you definitely have and they actually have numbers here too. So we saw underneath there. Beautifully placed. 550 nanometers for the green. And officially it's 546. Violets at 340. And 340, that's not on the spectrum there. What the chances of this red? 430, yeah. 430, and it was 435.8. And yellow was 580.
Which cost us?
579. For, yeah, the one above it. And helium, we had somewhere around 590, 600. We had 450.
It's hydrogen.
450, it says 450 green.
Oh, no, that is-
Color issue here. That's definitely not green there.
Yeah, that definitely is. Yeah, I thought it was.
We had 500, 501, and 680, and 6, this jive 670. Well, read that right. So from this, you can then think about the power of this. If each individual element gives off a particular spectrum, you can now look at any light source and start piecing it together. So if you look at our sun, obviously we're going to get a huge spectrum here, but some lights will be more dominant than others, and then you can start piecing together of, oh,
to get that spectrum, if we have 90% hydrogen and 10% helium, that's what it will look like, and, oh, okay. Now, that's not our sun's makeup, but that's, we get the idea, you can start to sort of mix and match and look at combinations.
So if you
What is
point
it?
that thing at the sun, and obviously not look at the sun, but look at the sun table, you'd be able to.
It would actually, with the naked eye, what you would see is basically the entire spectrum.
Okay.
But with more sensitive instrumentations, you can start to see some lights more, some bands more dominant than others.
What is it about uranium that makes it cover so much of the spectrum?
Alright, so what Bohr did is he figured out what is known as the first quantum level. You've taken chemistry, I think we've established, chemistry's been a while for anyone who's taken it.
Yeah, it's been a very long time for me.
There are these four quantum, what are called quantum numbers in chemistry, well, physics, and then chemistry, where no two electrons can have the same full set of quantum numbers. And so part of what you're seeing here are sort of hyperfine splitting that, yeah, they have the same first level quantum number, n is the same, but there are slightly different second quantum number, and so that's when you start to see, you know, things like this. The more protons that you have in the nucleus, the more complex it gets, and so that's why hydrogen is the simplest, and then it just gets more complex. Yeah, so that's hydrogen, helium, mercury. We're getting more and more protons in it, and so we get more and more lines.
Is it because there's more electrons, so there's more layers?
So yeah, you would get, that's part of it. But also, the potential energy formula that we used was for one proton, one electron. That's really nice and easy. Like once I throw in a third particle, say 2 protons and an electron, we now, the potential energy is actually a combination of all 3 of those particles. So you have basically 3 that you would add together. And uranium's got 92 protons and somewhere around 92. I think it's 92.
Yeah.
In theory, they all have the same number of electron levels. I guess the other part of it is that the more protons you have, I guess the farther out they can go without escaping, which I think is sort of cool,
Yeah.
to your point. All right. So hopefully this provides some credence to the fact that quantum physics does have some merits.
Yeah.
So one very well, what did you say?
I don't know.
Yeah, that's what runs through my head
Yeah.
every time I say it.
That's the only part that's on my, I don't know the rest.
So long farewell,
Auf
you say
Wiedersehen,
goodbye
goodbye.
to you, to you, to you.
Yeah.
Did you write things for everything like?
Cool.
Where does it go?
It would be halfway between, the intent was, I said halfway through the journey, I meant halfway between. So X would be, yeah, so that's my point.
Not here.
Yeah, so that would be,
Okay.
that, so, that right there.
Do you want me to stop this?
I would say yes.